So, good morning children. How are you all? Hope everyone is doing fine. Okay, come on, let's start with our session. We'll start with the lesson, actual lesson. In the previous two videos we had just the introduction. Now we start with the actual content of the lesson. Now before we study the actual periodic table, the initial part of the lesson deals with the theories of classification, the methods of classification that were given by the scientists, and each one of them had their own unique way of classifying the elements that had been discovered during their time. So we have to study first a few methods of classification that was done by the earlier scientists. Okay, so in the very first slide here you can see some scientists, Newland's octaves you can read. You can read the Debrisstriat's name, and then you can read Mendel's name, the one who had done a lot of pioneering work in classification of elements, and his periodic table had been accepted for a very long period of time. Okay, now we go to the next slide. Okay, the next slide doesn't have much to tell. It only deals with the initial methods of classification of elements, which we have taken up in Can you recall the various types of elements, that is metals, non-metals and metalloids. So this was the most ancient way of classifying the elements, that is metals, non-metals, and then there came another category that is of metalloids. So second slide only deals with the various classifications that was adapted by the scientists when the number of elements was very small. Okay, we move on to the next slide. The very first method of classification of elements was given by a German scientist, Debrisstriat. Now this was way back in 1817 when the number of elements was that were discovered was quite low, and so whatever elements were present at his time, he arranged those elements in groups of 3, and hence it was called as a triad. So Debrisstriat arranged the elements in groups of 3, and those were called as triad. So the term itself tells, no, that is triad. Tri means 3. So he grouped the elements in groups of 3. Now why did he make groups of 3 elements? How did he select those 3 elements? So Debrisstriat selected the 3 elements on the basis of the characteristics or the properties that were shown by those 3 elements. So he grouped, when he selected those 3 elements were similar in chemical properties. The chemical properties of all these 3 elements were similar, and so he made groups of 3 such elements which were having similar chemical properties. Then how did he arrange those 3 elements? So he arranged those 3 elements in increasing order of atomic mass. Now what is atomic mass? Atomic mass is the number of protons and the number of neutrons present in the nucleus of an atom. Now in those times, atomic mass was considered to be a fundamental property. Now what do you mean by a fundamental property? Fundamental property means a property which is going to be same for all the atoms of a particular element. A property that is same for all the atoms of an element. So in those times, atomic mass of an element was considered to be the fundamental property. But now if someone asks you that can atomic mass be considered to be a fundamental property? Now that you have already been acquainted, you have studied about isotopes. So isotopes of elements have same atomic number but different atomic masses. Like we have an isotope of chlorine, that is chlorine 35 and chlorine 37. So here we have that 17 is the atomic number of chlorine, but the mass is different. For one set of atoms we have the atomic mass to be 35, for another we have it to be 37. So how can atomic mass be a fundamental property? But way back then, during those times, atomic mass was considered to be the fundamental property, and so all the scientists of those times classified the elements according to the atomic mass. So again, going back to Debrisstriat's triad, so Debrisstriat selected elements with similar chemical properties and he grouped them into threes, and then he arranged them in the increasing order of atomic mass. Then what did he notice? Now as you can see on the screen that the rule has been stated over there, that is, when elements in these triads were arranged in the increasing order of atomic mass, it was found that the atomic mass of the middle element was approximately the mean of the atomic masses of the other two elements. Now this appears to be a very long statement, and let us understand the statement with the help of examples. So for examples we will go to the next slide. Right. So here we have Debrisstriat's triad. We have taken 4 examples in this slide. We shall begin with the very first example, that is lithium, sodium, potassium. So this forms a triad, that is a group of 3 elements, lithium, sodium and potassium. The next column gives you the atomic mass of each of them. Now what Debrisstriat said was, he said that the atomic mass of the middle element, that is sodium, is approximately the mean, arithmetic mean of the first and the third element. So let us find out, how do you find out the arithmetic mean? Mean in simple terms means average. So you have got here, you have to take the average of lithium, atomic mass of lithium and potassium. So you add up the two and you divide it by 2. So you have to just take the average. So when we find out the mean, that is, we have added 6.9 and 39.1. So the total becomes 46 divided by 2. That gives us 23. So we find that 23 is the arithmetic mean of lithium and potassium, and it coincides with the atomic mass of sodium, that is also 23. So Debrisstriat was correct here, as he had grouped the 3 elements, lithium, sodium, potassium, into a triad. Now let us just look into whether these 3 show similar chemical properties, because one of the criteria is that we have arranged them in the increasing order of atomic mass, which we can see here. Increasing order, you can see 6.9, 23 and then 39.1. But do they show similar chemical properties? Just ponder over this thought and just give yourself 2 minutes and just think about if they show similar chemical properties. Okay. So the one of the properties that we can easily remember is that lithium, sodium, potassium are all 3 metals. All 3 of them are metals. Another thing, another concept that you have studied in 9th standard is that of valency. Valency is determined by the number of electrons present in the valence shell of an atom of an element. So if you look into the electronic configuration, you will find that lithium, sodium and potassium, all 3 of them have got just 1 electron in their valence shell or the outermost shell. Since they have only 1 electron, they will show similar chemical properties. Similarly, you can even find out some more similarities between lithium, sodium and potassium. So here we have the first Debrisstriat triad, that is when elements with similar chemical properties are arranged in a group of three, that is a triad, in increasing order of their atomic mass, it is found that the atomic mass of the middle element was approximately the mean of atomic masses of the other two elements. Let us take up another triad. Here we have chlorine, bromine and iodine. Now how are these three similar? All these three are non-metals. They fall into a group of elements in the modern periodic table, and all of them are found one below the other, and they are all non-metals. They belong to a group which is called as the halogen group. So here we have the symbols chlorine, bromine and iodine. Now again we will take the mean of chlorine, atomic mass of chlorine 35.5, and that of iodine, that is first and third. You have to take the atomic mean of the masses of first and third element. So that gives you, the sum gives you 162.4, and that is to be divided by 2 again, and you are going to get 81.2. Now exact atomic mass of bromine is 79.9, but here we have got 81.2, but this difference can be ignored a little bit, and we can consider this also to be a triad. Coming to the next one, calcium, strontium and barium. So calcium atomic mass is 40.1, and that of barium, that is 137.3. So if you take the atomic mass again of first and third and you find out the mean, that is the average, sum comes out to be 177.4 divided by 2, that gives you 88.7 atomic mass unit. So this is 88.7. Actually strontium's atomic mass is 87.6. But again we find that the difference is very less, and that can be ignored, and we can consider even calcium, strontium and barium to be one of the triads. Again these three fall into the category of metals, calcium, strontium and barium, and you will even find that these elements have got the valency 2. Here in chlorine, bromine and iodine, all of them were non-metals and all of them were having valency 1. So valency is same, so we find that the chemical properties are also similar. Coming to the fourth triad, that is sulfur, selenium and tellurium. Now here we find that the atomic mass is 32.1 for sulfur, 127.6 for tellurium, and if we take the mean, you find that it comes out to be 159.7 divided by 2, that is 79.85, and actually it is 79. So also this difference can be ignored, and we can have sulfur, selenium and tellurium also to be of the Debrisstriat triad. So we have 4 examples. 2 marks question can be asked on this, and you will be asked to write down the law of Debrisstriat of triad, and you are expected to give even one example. So any one example you can remember and you can quote. Okay. Now we go to the next slide. Now children, in this slide you can see 2 more examples. The first example is of copper, silver and gold. Now copper, silver, gold, you know that they are all 3 metals. So they are having similar chemical properties. One property is similar, that is they are all metals. But when you work out the Debrisstriat's law for these 3, does it prove to be correct? Let us see. Copper atomic mass 63.5. The third one, that is gold, 196. 7. But when you add up the two, you get 260.5, and when you take the mean, that is you divide it by 2, you get 130.25. But now just see the actual atomic mass of silver. The actual atomic mass of silver is 108. Now here there is a lot of difference between the atomic mass that we have calculated using Debrisstriat's law and the actual mass of silver. So in this case, this difference cannot be ignored, and so copper, silver and gold cannot be considered to be a Debrisstriat triad. So as the atomic mass of the elements kept on increasing, it was found that the Debrisstriat's law was not obeyed. It was obeyed by those elements with smaller atomic masses. But as the mass went on increasing, this law did not prove to be correct. Similarly, one more example of zinc, cadmium and mercury is given. So zinc and mercury mean, when we find out the atomic masses, the total comes out to be 266.4 divided by 2, that is 133.2, but the actual atomic mass of cadmium is 112. Again, this difference is too big to be ignored, and so we find that this is also not a triad. So Debrisstriat's law of triads was obeyed only for certain elements. It was true only for certain group of elements, whereas it did not work out with the others. And so this method of classification could not be adopted. But it certainly gave impetus to several other scientists to do lot of research. It was a motivation for them, and so later on various scientists came up with various types of other classification methods. So one more such method that we are going to study is the Newland's law of octave. So for that we will go to the next slide. Right. Now the next method that was given by was John Newland. He was an English scientist, and in 1866 Newland gave us another method of classification of elements. So by his time about 56 elements had been discovered. So he tried to arrange those elements. His law is called as the law of octaves. Now octaves refers to the 7 notes, musical notes that there are there. If we take Indian music, then it's the 7 notes which are called as the saptak, correspond to sa, re, ga, ma, pa, dha and ni. So this group of 7 is called as the saptak. But when you recite them, what you do is the very first one, that is sa, gets repeated at the end. Means now it becomes a collection of 8 notes. That is sa, re, ga, ma, pa, dha, ni, sa. So this group of 8 is now called as the ashtak. So first note and 8th note is the same. That is, in this case it is sa. So Newland's law was based on these octave laws. So let us understand what this is. Now the next slide that you are going to see is just what you have in your textbook. I have picked up from the same textbook of yours. That is Do You Know, from page number 17. So let us see what is given over there. Here in this slide now you can see Do You Know. In Indian music system there are 7 main notes, that is sa, re, ga, ma, pa, dha, ni, and their collection is called saptak. The frequency of note goes on increasing from sa to ni. Then comes the sa of the upper saptak, at double frequency of the original sub. It means that the notes repeat after completion of one saptak. So every first and the eighth note will remain the same. The 7 notes in the Western music are Do, Re, Mi, Fa, So, La, Ti. The note Do, having double the original frequency, comes again at the 8th place. This is the octave of Western notes. Music is created by the variety in the use of these notes. So I hope you have understood the concept behind this. That is, the very first and the 8th are having similar, are the same notes over here. Now in the next slide, what I have given you is just a link. You can go to that link in YouTube. You can copy paste the link, and then you can see one video on it is based on the Western music notes, that is Do, Re, Mi, Fa, Sol, La, Ti, and there you can just enjoy the music and the Western notes, and you can even see how the first and the 8th note get repeated. Okay, visit this site and just see the video. Now for today we will stop here and we will resume back tomorrow. Your homework till then will be to just read the Debrisstriat's law and the initial part of the chapter, and just learn the law, Debrisstriat's law, learn one example at least of the triad, and the very first paragraph on page 17 based on Newland's law of octave.